So let's talk about the concentration of solutions using this first lecture worksheet for today. So this is 8.2 lecture worksheets. So yes, you are going to do a little bit of math. I'm going to get my calculator ready. You will need a little bit of calculation, little tiny. This is actually looking ahead, you know what? It's more the idea of first, we're going to, before going into the calculations, understanding what concentration means. So the concentration of a solution is how much stuff is dissolved in water, basically. And so the stuff that is dissolved is called a solute. And what does the dissolving most often is water. So the solute is dissolved in water, and then the whole everything together is a mixture called a solution. So a solution is a homogeneous mixture. In a homogeneous mixture, you know that there are different parts, but you can't see the different parts. It's uniform composition. So because you can't see the different parts, you have the concentration, which tells you how much you have of one part that you can't see in it. Okay. And so the units, just like you have units of measurement, length can be in meters or feet. Well, you have units of concentration that can be in different units. They're all equally correct, but they're just used for different amounts of concentration. So we've seen this before with air quality, the air pollutants, which are very, very low concentration, which is what you want for any pollutant. You want a unit that will be describing very low concentrations. And then you also have units that describe higher concentrations like percent or molarity. And so that's why there are different units for concentration. They are percent, parts per million, parts per billion, and molarity. Okay, so let me write all that. So you have percent, you have parts per million, you have parts per billion, ppb, and you have the uppercase M, molarity. And these are all units for concentration that you will see associated with describing how much solute is dissolved in a solution. Okay, so when we're talking about low concentrations, like a pollutant in water, these units of parts per million and parts per billion are the ones that are most useful. So we saw that for the air pollutants, and it's still true about the water pollutants, is that you want a very low concentration, or there better be a very low concentration of these pollutants in water. And so we're going to use a unit that will describe a low concentration. So for parts per billion and parts per million, so remember ppm is parts per million, and ppb will be less than that. That's parts per billion. So what that means in terms of concentration is you have a solution that has 1 million parts in it, and 1 part per million would just be one of those units in there. Parts per billion would be more dilute or less concentrated because you're taking a bigger sample, and you'd have just a number value describing a part in a bigger volume, a bigger sample, when you have 1 billion compared to 1 million. So then we'll also get into molarity, which is both this equation, this uppercase M, which is the unit, it's the unit molarity, this uppercase M, and it's also an equation, which is moles of solute divided by liters of solution. And really what you need to know is that this is the units, moles per liter, are equal to this uppercase M. And M is the word molarity. And molarity is one of the units for concentration. Okay, so that's what these are in the box, units for concentration. Okay, so let's understand then, when you have a 1.0 molarity solution of NaCl, what you have is NaCl is aqueous. That's what that means. Aqueous is something dissolved in solution. So AQ is a solute dissolved in the solution. And typically it's water that does the dissolving. Okay, so that means that what you have is not the sodium chloride as an ionic compound. What you have are separate ions. You have the sodium ion, the sodium plus ion that's aqueous, and you have also the chloride ion, Cl minus, that's also aqueous, AQ. So what you have actually, when you have a, when you pour salt, that's table salt, NaCl, when you pour it into water, you notice that it dissolves. What dissolving means is that the water molecules have gone in there and separated out the sodium ions from the chloride ions. So you can't see that white solid anymore because it's not a white solid. It's not NaCl anymore. They're separate ions that are too small now once they're ions. So that's what you actually have, is you have ions in the solution. You don't have the entire compound. And so that's the ionic compound that you don't have. What you have instead are these individual ions. Whoops, I just lost that. Everything that I just wrote, I just lost. Sorry. So NaCl, let's write what you need. Aqueous is really Na plus aqueous plus Cl minus aqueous. Okay. And what I just lost it again. Come back. NaClAQ. I think, okay, let's try to do this again. No. What I want is to switch to the red color and not lose all this. Okay, I guess I'm not going to switch to the red color. I'm going to write this a third time. All right, so what you actually have are these ions in solution, but you don't have that NaCl. So I'm actually going to cross that out like that. Okay, so the concentrations though are that if you originally have 1.0 molarity of this original ionic compound, well, when this breaks up into the ions, you will have 1.0 molarity of the sodium ion and also 1.0 molarity of the chloride ion. Okay, and so this is an equal concentration of each of these because when NaCl breaks up, you have one of each of these. So the ratio of this NaCl will break up and give you one of each of those. And so the concentrations are going to be unchanged. So the concentration of chloride ions is 1.0 molarity of the chloride ions. But things are different when you're talking about CaCl2. So this is also an aqueous solution that when this breaks up, okay, you have the calcium ion, which is not just calcium plus ion, it's a +2 ion. And so this is aqueous. And you also have the chloride ion, and that's aqueous. So it's, you have these ions in solution, but you don't actually have this ionic compound in solution. Okay, you have those ions, and when this breaks apart, because of the original chemical formula having a subscript 2, it means you're going to have 2 of the chlorines for every one of these, the one unit of calcium CaCl2. You're going to break up and have one of these calcium ions, which is a +2 charge, and 2 of these chloride ions, because each one is a -1 charge. So the concentration of chloride ions is actually twice as much, 2 times that 1.0 molarity, which is going to be 2.0 molarity of the Cl minus ions. Those are the chloride ions. Okay. But when you have a concentration of the solution that's 0.5 molarity, so 2 times the 0.5 molarity original solution, instead of 1.0, it's 0.5. Well, now you have a 1.0 that calculates out 2 times 0.5. So it depends on the chemical formula, how many ions you will get when this ionic compound breaks up, and then also the original concentration of the solution. Here it was 1.0, so 2 times 1, but here it was 0.5. All right, now let's look at this next question, which talks about the maximum contaminant level. So the maximum contaminant level for mercury in drinking water, that's a level that's set by the EPA. It's 0.002 milligrams per liter. And then they're asking you, what is this in parts per million ppm? So going back up to here, we actually have a conversion for this. 1 ppm is 1 milligram in 1 liter. Or you can have the ppm, the units of ppm equal milligram per liter. And so if we want to take this 0.002 milligrams per liter, well, that this is equal to 1 ppm. Since 1 milligram per liter equals 1 parts per million, that means that we can write that this is 0.002 parts per million. Okay, and so when you have the next question, which says a 5-liter sample of water contains 80, and remember that's the metric prefix micro. So this is micro, that's 10 to the minus 6. This is micrograms, okay? Express the mercury ion in concentrations of ppm and ppb. So first of all, let's go back and we have that ppb, okay, I just got everything back somehow. I don't understand what I just did there, but parts per billion is what I just got back. I'm going to erase this. Parts per billion, ppb, is the units of microgram per liter. That's that micro, 10 to the minus 6. So if you have, this is not given to us in micrograms per liter. So in order to get ppb, which is micrograms per liter, we're going to have to do a little bit of math here. So I've got 80 micrograms in 5 liters. That's what it says. You got 5-liter samples and it has 80 micrograms. So you're going to have to do a little bit of math to get to the units of micrograms per liter and a little bit of calculator, which is 80 divided by 5. So this is 16 and micrograms per liter. So because since 1 microgram per liter is equal to 1 parts per billion, 1 ppb, we are going to have this as 16 parts per billion. Okay. Now, if you want to get this to parts per million, remember the stepwise conversion to get from parts per billion. So I'm going to go here. So 16 parts per billion means that you have 16 in a billion, which is 10 to the 9. So if we want to get this to parts per million is how many parts in 10 to the 6th. So remember the stepwise conversion from parts per million to parts per billion or to percent is this is going to down to dividing by 10 each time. So this would be 1.6 in 10 to the 8th and dividing by 10 again, 0.16 in 10 to the 7 and dividing by 10 again to get to 0.016 in 10 to the 6th. And so that means that is 0.016 parts per million. Okay, and so that's why we have the different units. The units of parts per million, which gives us in fractional, the decimal places, 3 decimal places out, is not as good as having this just as the whole number value, 16 parts per billion. So having a different unit, parts per billion, which is for lower concentrations, is more useful than having the parts per million units for the same number value, because then you're dealing with a fractional or decimal number. Okay. So then the next question is the sample in compliance with the MCL? So let's see, what was that MCL again? Let's see if I can switch yes, I can switch the colors again. So the MCL, the maximum contaminant level is 0.002 parts per million. And does this fall in the range? So 0.016 parts per million compared to the 0.002 parts per million MCl. Okay, so this is 0.016 is greater than, right? So this is greater than parts per million, is greater than the 0.02 parts per million. So when the number value, the tested sample of water is a higher parts per million, that means it's not falling in the range. So this is higher than the maximum contaminant level. Okay, so that means it's not in compliance. And that would be a flag. There's too much of this pollutant in there. Okay, so let's take a look at this next real world problem. The acceptable limit for nitrate ion, often found in well water in agricultural areas, is 10 parts per million. If a water sample is found to contain 350 milligrams per liter, does it meet the acceptable limit? So in order to compare these, you need both of these in the same units. So we have the MCl for the nitrate ion is 10 parts per million. So let's take that water sample, which is 350 milligrams per liter. And remember, the 1 milligram per liter is 1 part per million. So that means 350 milligrams per liter is 350 parts per million. So then let's compare those number values. So you have the maximum contaminant level, 10 parts per million. And then you have the 350 parts per million, and that's the sample value. Okay, so this is the 10 parts per million is less than, or you could say the 350 parts per million is greater than. Okay, and so this means that this is greater than the MCl. 350 is a lot more than the 10 parts per million. So that means that this is not in compliance. That you're looking at a water pollution issue there. Okay, sound good? Of acids. So this is a little offshoot of nomenclature. So writing the chemical names or writing the chemical formulas, we've already covered for ionic compounds or covalent compounds. Well, acids are a special category of nomenclature. Acids are aqueous solutions. So acids are also ionic compounds. They are ions dissolved in water. And let's also write that. So acids are always aqueous solutions. You're never going to come across an acid as a solid. It's going to be dissolved in water. I mean, if you do come across, let me know. So when you have the ionic compound, those ions are broken apart and it's to different degrees. So that was strong acids are completely dissolved and all ions. Weak acids are not completely dissolved, and instead you actually do have the whole compound, but it's still dissolved in the water. And so the same is true about weak bases and strong bases. And we will see acids and bases. We'll review all that in an upcoming lab. So there are these upcoming labs that we'll still be catching up on for this module 8, which are these aqueous solutions that can conduct electricity, so testing conductivity, and also we're going to look at acids and bases. And so we need to understand how to write the chemical names and chemical formulas for acids. So they have a special set of steps because acid is always going to be in the chemical name. Okay, and so that's a little different from ionic compounds. For ionic compounds, you have the ions and you write the names of those ions. For acids, there's a little bit difference here. So let's start with step 1. When you have an acid, you're talking about something that always has hydrogen, the hydrogen cation. So H plus is always going to be the positive charge ion, the cation, okay? And so you will always see hydrogen as the first element in the chemical formula. So the acid chemical formula will always have hydrogen as the first element. And that hydrogen will have a subscript or not, depending on the crossover rule from the anion, from the negative charge. So for example, HCl does not have a subscript. That's because the chloride ion has a negative charge, a -1, and there's no 1 that's written as the subscript, compared to H2SO4. So H2SO4, you can see hydrogen is the first element, but there's a subscript 2. That 2 is crossed over and down, and it came from the sulfate anion that is SO4 with a -2 charge. And so this next chemical formula, H3PO3, has the 3 subscript. So hydrogen is still the first element, but that 3 subscript came from the chemical formula of this polyatomic ion that you are not familiar with, but it is phosphite PO3 with a -3 charge. So what you have is an acid formula, and you want to take that acid formula and split it apart into ions. So what that means is, let's take that HCl, and you want to split that apart by writing it separate. Write the 2 element symbols separate. If you have a polyatomic ion, you're going to want to put parentheses around the polyatomic ion before you split it apart. Okay, and so that's what that says. Then you add the charge sign, step 3. So the cation is always first and the anion is next. So you're going to add a plus and a minus. Okay. And then you use the reverse crossover. What that means is you pick up any subscripts and those become superscripts. So this example of H plus and Cl minus, there are no subscripts. So you don't have any superscripts that become charge values. So you just check that these charge values are correct. How do you check that? So this is where you use the periodic table family numbers. Remember, the family numbers are that if you're in family 1A, it should be a +1 charge. 2A should be a +2 charge. And 3A should be a +3 charge. Then you have 5A, 6A, and 7A. So 5A should be a -3 charge, 6A should be a -2 charge, and 7A should be a -1 charge. Or you're going to use the polyatomic ions list. And it should be the correct chemical formula with charge. Okay, so you still need those polyatomic ions, the chemical formula, and the charge has to be correct. That's what that means if you're if you have a polyatomic ion, or if you just have an individual atom like this example. This is chlorine, and it is in family 7, and so that means it should have a -1 charge, and so that is not -2, not -3, because sometimes these numbers get picked up if they were part of a polyatomic ion. Okay, so we checked that that's correct. This hydrogen should always just be plus or +1. So both those charge values are correct. So then here's where you diverge, is that you want to write the name of the anion. This should be a number 5. Write the name of the anion. Okay, so I'm going to circle that name, that anion first. And this anion is Cl minus. So Cl minus, what is the name of that? Well, that, remember, is when you have an individual atom, which was chlorine. When you have an individual atom that forms the negative charge, or the anion is the negative charge, it has the IDE name ending. So it's not chlorine, the element, but it's chloride when it is the negative charge anion. Okay. Now, why that's important is because this will guide the next step, which is the ending of that anion name will get you to the acid name ending. And for this case, also a name beginning. So when you have the IDE name ending, you take the part which is not the IDE name ending. So this part, CHLOR. And before it, you have hydro. And after it, you add the ICE or ic acid. So IC and then acid. Okay, and you will see that in all these name endings, and this is the chemical name, all of these chemical names always have acid as part of the name. And that's why this process is different. Normally for an ionic compound, you figure out the ions and then you write the names of those ions. Well, this is not the name of chloride that is used. Instead, what's used is the beginning hydro and then the ending ic acid. And the reason is that so that you always have this acid highlighted as part of the name. So basically you walk into your chemical stockroom and you see this section is all called acids, and those are potentially corrosive and dangerous. So that was set up purposely so that acids would be easily identified by their name. Okay. And so this is these examples. Let's take a look at HNO3 with these steps. So you first want to look at the chemical formula and write these ions separate. So I can first say that this is a polyatomic ion and put parentheses around NO3. So then when I separate this, I'm going to write H and then in parentheses NO3. Then you're going to add a plus and a minus. So the positive is first and then the minus. And you can see because of this parentheses around the NO3, highlighting this in green, I don't get to take that 3 out of the parentheses. Remember, the parentheses means don't touch this. Don't take anything out. Don't put anything in. And so that means there's no subscripts to pick up to become superscripts. Okay. And so therefore, we're going to check the charges. Hydrogen is +1. And this is the correct chemical formula and charge for the nitrate ion. So that's called the nitrate ion. That's the name of that anion. This is the name of the anion. And that's on your polyatomic ions list. So when you're looking at the name of that anion, you need to look at the name ending. It's ATE. And so for the name ending ATE, okay, let me erase some of this. The name ending ATE aligns with this, which is you take this original part of the name and you add a new name ending ic acid. So what's the original part of this name? It is NITR. So I'm going to take this NITR and add a new name ending, which is this ic acid. So NITR and then ic acid. And that's the chemical name of HNO3. It's called nitric acid. Okay. And so the next example is HNO2. So let's take a look at that and first identify that there's a polyatomic ion NO2. So put parentheses around NO2. And so when you split this apart into H plus and then parentheses NO2 and then a minus. So I put a plus and a minus. And then you got to determine the name. What is the name of this NO2? So going to your polyatomic ions list, you would find that this is nitrite. So the name ending is very close to nitrate, but this one is nitrite is the name ending ITE. So you take that first part, which is NITR, and you add a new name ending onto it. So if it's an ITE name ending, going back up to this list, in green, the ITE name ending, you change it to OUS and acid. So that's called nitrous acid. Okay. So let's take a look at the next example. Now I'll pause right now and tell you, yes, I know that you could easily just put this in a Google search and write, what's the chemical name of this HCl? But I also know that you can do this because this is not that bad, right? So you have H and Cl, H plus and Cl minus. And so you split this apart. This is the correct chemical, the correct chemical formulas and charges. This is hydrogen is a +1 and chlorine is always -1. Oh, we already named this one. So let me show you this though again, is that you have the name of this ion is called chloride. And so because it has the IDE name ending, you want to take the first part of it, which is CHLOR, and add a new name ending to it. So IDE, you're going to add the ic acid, but you also need to add the beginning part, which is hydro. So not just chloric acid, but hydrochloric acid is the chemical name when you have this anion Cl minus. Okay, now let's take a look at H2SO4. So for H2SO4, what I first want to do is put parentheses around that SO4. So when I split this apart, this is going to be an H and an SO4 in parentheses. Okay, so then you have a plus and a minus, and this is one that does have a subscript. See that two hanging out down below next to the H? That becomes a superscript. So that's a subscript that you pick up, and it becomes a 2 here, or specifically here. So it's SO4 with a -2 charge, which is called the sulfate ion. Okay, so SO4 -2 charge is the sulfate ion. So now you want to take a look at the name ending, which is ATE. And that ATE name ending means you get the rest of it, which is SULF. And you have the name ending ic acid. But let's add this, I'm going to switch to red here, is when you have sulfur or phosphorus, you actually need to add in a few extra letters. So if you have sulfur like this, sulfur, or phosphorus, that would be the element symbol P. If you have sulfur or phosphorus as part of your acid, then you need to add a few extra letters in. For sulfur, you need to add in an extra UR. So I'm going to add in that extra UR before I add the name ending, which is this for ATE, the ic acid. So this is sulfuric, and then acid is the name of this H2SO4. So not sulfic acid, you need to add those extra letters UR. Okay, you guys feel like you can do this? Yes, okay, good. So let's take this the other direction. And if you're given the name of an acid, you can write its chemical formula. So this is kind of the reverse. But when you're given an acid and you know that you have an acid, because it has acid in the name, let's take, for example, hydroiodic acid. Okay, so because it has acid in the name, you want to write the chemical formula from that. Okay, so this is a different series of steps than an ionic compound. Normally, if you're given the chemical name, you write the ions and use the crossover rule. So this, you need to figure out from the name ending, whether it's ic acid, OUS acid, or hydroic acid. You have to figure out what the anion is. Okay, so the anion of this hydroiodic acid. Well, I can see from the beginning, which is hydro and then an ic acid, that this is the part that's left. So I take that iode, and if it was a hydroic acid, that name ending is corresponding to the IDE. So remember, hydroic acid is an IDE name ending for the anion. The OUS acid is an ITE name ending, and the ic acid is the ATE name ending. Okay, so I'm going to add to the original part. Let's make this purple here. So this, or IOD, I'm going to add IOD with the name ending IDE. Okay, so this is the iodide, is the name of the anion. So that's the name of the anion. So we want to write the chemical formula of that anion. And so that is the iodine is the element. When it has the IDE name ending, it means it's the single atom formed the anion, the negative charge. So that's I minus. So now you need, for the negative anion, a partner. You need the cation, you need the positive charge. Well, for acids, the cation is always H plus. So you want to write these next to each other, but the hydrogen H plus is always going to be first. The positive charge is always first. So write HI or H plus with the I minus next to it, and then use the crossover rule to write the chemical formula, which is HI. So you get rid of the plus and minus signs, and there's no numbers that cross over and down. So let's take a look at this next example, which is hydrofluoric acid. So hydrofluoric acid, notice that there's a hydro and ic acid. So take what's left, which is the FLUOR. From the beginning and ending, the hydroic acids are the name ending IDE. Okay, so I'm going to add IDE, and that's fluoride is the name of the anion. So what is fluoride? Well, it comes from fluorine, which is the element symbol F. The IDE name ending means it's the single atom formed the single anion, monoatomic anion. So this is the F minus ion. And then the positive is always going to be H plus. The cation is always hydrogen ion. So H plus, F minus, the crossover rule will end up with HF, and that's your chemical formula for hydrofluoric acid. For sulfurous acid, so you want to notice the name ending is OUS acid. So let's take this, is sulfur is the rest of the word, okay? And when you have sulfur or phosphorus, I'm going to underline this in red. If you have sulfur or phosphorus, you need to remove those extra letters. For sulfur, you're removing the UR, okay? And that's because this is the reverse of that. So we added the UR when we were writing the name, but now we're removing the UR when we're writing the anion chemical formula. So instead of sulfur, you're going to have just sulf, okay? And this is now adding what goes with the OUS acid. The name ending for OUS acid is this ITE. So ITE is the name ending. Sulfite is the anion name. So we want the chemical formula for sulfite. Where are you going to find that? If you have it memorized, from the polyatomic ions list is where you're going to look. If you don't have it memorized, sulfite is SO3 with a -2 charge or 2- charge. Okay, so it's very close to sulfate, which we looked at earlier. Whoops, sorry. So what is the positive charge? It is the hydrogen ion is always the positive. And so now you want to use the crossover rule, which is that 2 crosses over and down, and the plus and minus signs are gone, and you don't need the parentheses because you have nothing that crossed over and down to here. So when you have no number outside of the parentheses, you can get rid of the parentheses. And this would be the chemical formula for sulfurous acid. Okay, now let's look at the last one, which is acetic acid. So acetic acid, you want to notice actually the name ending, which is ic acid. Okay, so take the first part of it, which is ACET, and rewrite ACET. And the ic acid name ending here, let me erase some of this. The ic acid name ending is going back to here. The ic acid is a new name ending ATE. Now I don't need to remove any letters because it's not sulfur or phosphorus, but I do need to add the ATE name ending and look for the acetate anion. So this is going to be on the polyatomic ions list, and this is that C2H3O2 negative charge. This is the most complicated polyatomic ion, and it's hopefully something that you're more used to now. So that's the negative charge, that's the anion. So the positive charge is always the same. You want to put in front of it H plus. Using the crossover rule, you would write H and then C2H3O2. And I wanted to add the parentheses there so I can show you, you can take away the parentheses because there's no number outside of the parentheses. Okay, so this would be the correct chemical formula for acetate. And I know that if you look, for acetic acid, I know that if you look up what's the chemical formula for acetic acid, you'll get something that looks different. But if you're following the polyatomic ions list for Chem 9, this is the correct answer. So this is one where you are not going to break into the parentheses, even if the parentheses are not there. So don't combine the hydrogens. So don't make it H4. Okay, that's because even though I got rid of the parentheses for this chemical formula, they're still there. They're just there in spirit. That is a polyatomic ion where you're not allowed to change anything or take anything out or put anything into the parentheses, even if they're not there. Sound good? So let's get through this worksheet and actively work on figuring out the complete ionic equation and then you basically start getting rid of spectators to get to the net ionic equation. So this all falls into the aqueous solutions to start with. And remember, the ionic compound, when it's dissolved, you have aqueous ions, and it's called an aqueous solution. And you can write the ionic compound as separate ions. Okay, so that was in that very first worksheet from today. And so instead of table salt, when it is dissolved in water, is NaCl aqueous. You don't actually have those ions. What you have are these ions that you can't see anymore, Na plus and Cl minus. Okay. And so basically anything that is a solution with the AQ physical state. And I remember going back, how do you know if something is aqueous? Remember, that goes back to solubility rules. So the solubility rules will tell you if a solution is dissolved, and that would be aqueous, or not dissolved, and that would be a precipitate or a solid. Okay, so just focusing on those that are aqueous, when there's the AQ physical state, you can break apart the ionic compound into the individual ions, and both of those ions, you notice, are also the AQ physical state. That means that they're still dissolved in the solution. Okay, and so if you have a polyatomic ion as part of the ionic compound, when the ionic compound breaks apart, it doesn't break apart into separate atoms. You have to put a parentheses around the polyatomic ion, like this NO3, and this breaks apart into the polyatomic ion, which is now in the parentheses NO3, and the other ion, which was not, the Na plus. And so notice that this, because it was AQ, you can break this apart into the separate ions. Okay, now this is also something we saw earlier, but this becomes more important now, is that any subscripts that are part of the chemical formula, those get picked up and become charge values. And they also, okay, so they become charge values, that's one, but they also become coefficient values for the other ion. So there's two things that happen to a subscript. So this is a subscript, I'm going to circle this in red. In the chemical formula, that 2 becomes two things. It becomes a charge value, and it also becomes a coefficient. So notice that subscript 2 becomes the charge value plus 2 on that ion because it crossed over and up. Okay, so that's the magnesium plus 2 ion. The other thing about that 2 is it becomes a coefficient, circling this in 2. It becomes the number value telling you that you needed 2 of the other ions, and that's what cancels out to form the chemical formula, which is neutral with no charge. Okay, so but what you need for this is that when you have an aqueous solution, anytime you have the AQ physical state, you can break apart the ionic compound into ions. But when you have a subscript, that subscript needs to go 2 places. It becomes a charge value and a coefficient. Okay, and so we're going to be seeing balanced chemical equations are the starting point. So the balanced chemical equation that gives you chemical formulas, reactant side, product side, and also coefficients. Okay, but you're going to take that balanced chemical equation and turn it into a complete ionic equation. And so that is anything that is an aqueous ionic compound, anything with an AQ physical state. So you break apart anything with an AQ physical state into the ions. Okay, so that's what we have here. In this process, let's circle in purple the physical states that are AQ. This HCl, this NaOH, and this NaCl. Anything that is not the AQ physical state, like H2O liquid, you don't break apart. Okay, so breaking this apart into the ions, you will end up with, this is the hydrogen and the chlorine. H plus and Cl minus is what comes from this HCl. The NaOH, you also need to break apart into ions. So in the complete ionic equation, you're going to end up with the Na plus and also the OH minus. So notice you need a parentheses around the OH. It doesn't break apart into separate ions. And this is Na plus aqueous ion and OH minus aqueous ion. Okay. H2O, Don't break apart. Why not? Because it has the L physical state. The only thing you break apart is the AQ physical state. Okay, so then NaCl does have the AQ physical state. It's aqueous. So you want to break that apart into the ions, which are Na plus and Cl minus. Okay, so that's called the complete ionic equation when you take any of the aqueous ionic compounds and break them apart. The net ionic equation is basically getting rid of any spectator ions. And a spectator ion is when you have something that's exactly the same on both sides of the reaction arrow. So that's the same on the reactants and products side. So let's circle in green exactly what's the same. What is a spectator ion that's exactly the same? So I can see that this Na plus is exactly the same on both sides. You have to have the same charge value and the same physical state AQ. What else is the same is the Cl minus. It is exactly the same. The Cl minus and the AQ, they're exactly the same. H plus is not the same because it becomes H2O, right? And OH is also not the same. So basically you get rid of those spectator ions and you keep everything else, which means you carry down the H plus, you carry down the OH minus, and you carry down the H2O. And that would be called the net ionic equation, is getting rid of all those spectator ions and only writing what's left. Okay, so now let's give it a shot here. So down here, you want to take this, first balance it, then write the complete ionic equation and then the net ionic equation. So first, let's check that this is balanced. You have sodium on both sides, you have chlorine on both sides, you have this nitrate ion on both sides, and you have silver on both sides. So this is already balanced. Don't need to add any coefficients. For the complete ionic equation, you take anything that's AQ and you break it apart into the ions. So this is going to be Na plus AQ and Cl minus AQ, breaking this apart. Okay. The next one is AgNO3. When I break this apart, I first want to recognize that this is a parentheses needed around NO3. So when this comes apart, it is going to be Ag plus, that's an aqueous ion, and then in parentheses, NO3, that's minus as an ion. And then on the other side, so now we're at the arrow, and on the other side, you have NaNO3, which also gets a parentheses around that NO3. Okay, so you want to write Na plus AQ, and then in parentheses NO3, and then that's minus AQ. Moving this up. You have next the AgCl. That has the physical state S. So that means don't break it apart. Just copy it exactly like that, AgClS. Okay, don't break apart anything that's not AQ. So now let's figure out what's exactly the same on both sides. Let's circle in green things that are exactly the same. So that's Na plus is exactly the same. You have to have the charge value and the physical state AQ has to be exactly the same. What else is exactly the same as this NO3 minus? Charge value and physical state exactly the same. So those are the ones you can get rid of. And when you write this, write what's left. This is Cl minus AQ plus the Ag plus AQ. And then on the other side of the arrow, AgClS. And that's called the net ionic equation when you write what's left. Okay, let's take a look at the next example, which is H2SO4.
I have a question.
Yes.
So how come we can't get rid of the AgCl?
Because it's not exactly the same. So this is AgCl. First of all, we can't split it apart because it has the S physical state. Okay, and Ag is Ag plus with the AQ physical state, which is different from Ag here that's part of the compound and has a different physical state. Same thing about Cl minus. Cl minus is the element symbol Cl, but it also has the charge value minus, and it also has the physical state AQ. And that is different. That's different from the Cl, that's the element symbol, but that has a physical state S.
Okay, thank you.
Okay, thanks. Okay. So Let's take a look at the next one, which is this equation is not balanced. So I can see that I want to write above H2O, H and OH. Okay. Anytime I'm trying to balance something with H2O, I want to write HOH because that will show me that I have one hydrogen and one hydroxide in H2O. So on the left side, on the reactant side, I have one OH. That's fine. But the problem is I need two hydrogens. So I'm going to need a 2 coefficient in front of H2O. Okay, so that means I need 2 of those hydrogens. So that's why I put a 2 there. That was because of H2. So what that means is I've got 2 hydrogens, and that checks off that box. Okay, so don't be fooled in thinking that it's 2 times H2. You don't have 4 hydrogens. You have 2 hydrogens, and you have 2 hydrogens that are part of OH. Okay, so you also have 2 OHs. That's what that means. So you have in green 2 OHs. So I'm going to need 2 of those OHs on the reactant side, on the left side. So I'm going to add a 2 in front of KOH. And that 2 means I also will have 2 potassium. And so that's the K2 that's covered there. There's also 1 sulfate on both sides. And so now this is balanced. Okay, so remember that little trick is when you have H2O, write it as HOH. All right, so now the complete ionic equation is you take anything that has the AQ physical state, that's H2SO4, that's KOH, and that is K2SO4, and you break it apart into the ions. Now we have subscripts and coefficients going on here, so that's going to be a little bit more going on with this one. So first of all, you have H2SO4. There is a parentheses that I need around the SO4. And I also need to pay attention to, in red, that subscript 2. Because remember, subscripts become a charge and also a coefficient. So this is going to break apart and become H plus AQ and SO4. And so this is AQ. And so this 2, remember that 2 that that's red, becomes a coefficient. It's a 2 in front of H plus, and it's also a -2 charge, becomes the charge value on SO4. Has to go 2 places, coefficient and charge value. Okay. The next one is you have this coefficient 2 that I'm going to circle in purple. That coefficient gets carried through to both of those ions. So let's write this out. First, I have that this is OH. I'm going to put this in parentheses. Come on, pen, come back. Okay. This is, put this OH in parentheses. It doesn't break apart into separate atoms. So you're going to have the K, it's AQ, and then OH in parentheses, and that's AQ. Okay. But the coefficient that I circled in purple, it carries through to both the K, so 2K plus, and also the other ion, the hydroxide, 2OH. Okay, so the next is you've got the arrow. So the reaction arrow. On the other side of the reaction arrow is 2H2O. Don't change anything about that. Just write it exactly as it was because it has the L physical state. And then you've got K2SO4. Because of the AQ physical state, I want to first put a parentheses around SO4. And also notice that outside of the parentheses is that subscript 2. So remember what happens to subscripts, they become a coefficient and a charge value. So when I split this apart, it's going to be K with a plus charge, that's AQ, and then in parentheses SO4 with a minus charge, that's AQ. And that 2 coefficient, or that 2 becomes the coefficient 2. There's 2 of those Ks, and then this also picks up and becomes a charge value, and it's -2. And that's the correct formula and charge for the sulfate ion. Next, let's circle exactly what's the same on both sides. And exactly means it has to have the same symbol, has the same charge value, the same physical state as well, and also the same coefficient. So this is an example here. You've got 2 of the K positive charge ion. You need to have 2 of those also. Okay. And only then can you get rid of it. What else is exactly the same? This SO4 with the -2 charge, it's aqueous, is exactly the same on both sides. Okay. And so what you have left is what goes into the net ionic equation, which is 2H plus AQ plus 2OH minus AQ. And this goes to 2H2O liquid. Because those are all twos, 2, 2, and 2, you could reduce it down, but we won't need to worry about that right now. Hopefully you guys understand writing the ions for the complete ionic equation. That's the hardest part of this. Okay, let's take a look at this next example. Okay, so we've got a chemical formula that appears to be balanced. Let me check. So I'm going to write above H2O, HOH. And there's 2 of those. So I need 2 hydrogens and 2 hydroxides. So there are 2 hydrogens because of 2 HCl, and there's 2 hydroxides because of that subscript in BaOH2. So this is already balanced. So no need to balance this one. In writing the complete ionic equation, you take anything that's AQ physical state. So this is HCl, BaOH2, and BaCl2. Take those and you're going to break those apart. And so we need to pay attention to subscripts and to coefficients. So this has the 2 coefficient. And so when this breaks apart, you're going to have H plus AQ and Cl minus AQ. Because of this 2 coefficient, because of this 2 coefficient, you need 2 of each of those ions. That 2 carries through into both ions. Okay. For the next one, you're looking at BaOH2. So when this breaks apart, you're going to have Ba plus AQ, and then OH in parentheses, that's a minus, and that's AQ. And circling in red, this is a subscript 2 that has to go 2 places. It becomes the charge value, or the +2 charge on barium, and it also becomes a coefficient, a 2, in front of the OH minus ion. Okay, so next is we've got the arrow, and the arrow is on the other side, 2H2O. So don't change that, just write it exactly, 2H2O with the physical state L. And then the next thing you have is BaCl2. So that's aqueous. So you want to break this apart into Ba plus AQ and Cl minus AQ. And there is a subscript. That 2 in that chemical formula means it has to go 2 places. It becomes a charge value for Ba. So that becomes +2. And it also becomes a coefficient in front of the chlorine. There's 2 of those. Okay. So now we're going to circle exactly what's the same. So this is exactly the same. 2 and the Cl minus and AQ has to be the same coefficient, the same charge value, and the same physical state in order to cross it out and get rid of it. The other thing that's exactly the same is Ba plus 2 with the aqueous physical state. That's exactly the same on both sides, so you can get rid of it. And in the net ionic equation, what carries down is 2H plus AQ plus 2OH minus AQ. And then on the other side, you've got the 2H2O. And that would be your net ionic equation, which, because those are all 2s, you could reduce down, and I'll write this one this time. And this would be H plus OH minus AQ is H2O liquid. And this is called a neutralization reaction, when at the heart of what's going on for what is a double replacement reaction when water is formed, and we're going to get back to double replacement reactions next week. This is really what's going on in a double replacement reaction when you have water as a product.